Hello everyone, I'm Peng from Peking University. I'm excited to be here to introduce our work, XHarvest, which is the high-performance and cost-efficient SSD architecture with CXL-driven harvesting. The latest PCI Exi SSDs can deliver more than 10 GB per second bandwidth. This high performance makes them adopted across diverse computing domains such as AI and ML workloads. Achieving this high performance requires the SSD to aggregate numerous storage resources, notably hundreds of NAND flash drives concurrently operating. And the SSD also demands substantial computation and resources to accelerate the firmware execution, such as the flash translation layer. For example, PCI Exi SSDs requires 4 times more computing power compared to PCI Exi SSDs. They also require extensive DRAM to accommodate the entire metadata, with 7.5 TB SSDs typically requiring 10 GB DRAM. However, we observe a critical cost utilization dilemma emerging in high-performance SSD designs. SSDs reserve costly resources to serve the I/O burst, like 13% of the total cost for computation and 10% for DRAM. But the occasional nature of I/O burst in the data center result in serious resource underutilization. For example, a long-term study in Alibaba observed that over 96% of the operating time, the I/O bandwidth utilization on their servers is below 25%, showing that the SSD internal computation and DRAM resources are often idle. This dilemma drives SSD designs toward both cost-efficient and high performance. One of the pioneering architectures towards such a goal is the open-channel SSD. OCSD removes the SSD internal computation and DRAM resources, but rather leverages the host side resources for firmware execution and metadata. However, this architecture faces adoption obstacles. The OCSD simply replaces the SSD internal resources with host resources, which introduce the host side resource contention with user applications. Specifically, OCSD statically reserves excessive host memory for metadata, especially when deploying multiple SSDs, such as the common 24 SSDs equipment in current storage servers. This significant memory reservation competes with user applications, as user applications are also memory intensive. For instance, applications on the Alibaba servers always consume more than 19% memory capacity. Moreover, by delegating firmware execution to the host, OCSD also leads to the CPU contention, as applications simultaneously utilize the host CPU for their computation. We observe that applications maintain high CPU utilization even under moderate I/O loads. Our observed resource utilization characteristics in data center implies a dynamical resource exploitation method to address this challenge. Our analysis reveals that the number of I/O active virtual machines concurrently exceeding 5 occurs only for 2.20% of the runtime. This indicates that the I/O burst occurs occasionally on a minority of SSDs, while the majority remains idle. Such burst interleaving implies slight resource demands concurrently. Therefore, we can utilize host resource dynamically and on demand for I/O burst, known as host resource harvesting. We'll provision moderate SSD internal resources for regular I/O loads to isolate the SSD and the user applications. Based on the analysis, we can propose a straightforward solution for the high-performance and cost-efficient SSD architecture. However, such solution still faces challenges. While the harvesting mechanism requires tight collaboration between the host and the SSD, the existing PCI interconnect has become the obstacle. Specifically, PCI separate the host and SSD into different cache coherency domains. This prevents the host from directly accessing the SSD internal resources, such as retrieving the metadata from the SSD internal DRAM. Our key insight for tackling this challenge is the emerging CXL interconnection. CXL integrates the host CPU and SSD within a unified cache coherency domain. This allows them to use simple load store instructions to directly access the unified memory space with fine granularity. This tight integration can streamline host SSD collaboration. This naive solution is also vulnerable to security issues. In particular, the unprotected firmware execution on the host presents sensitive firmware leakage risk, forcing the SSD vendors resist integrating their proprietary firmware into the open source IO stack. This limits the future enhancement and the broader adoption. TE technicals such as the Intel SGX offer a promising solution to the firmware leakage risk. TE enables secure program execution in an isolated environment like enclave on the host. By executing the sensitive algorithms in the enclave, SGX protects the code and data from unauthorized access by any software or even the operating system, thus avoiding the potential leakage risk. However, our preliminary study reveals that directly porting the FTL algorithm into the enclaves suffers from serious performance issues. The direct porting results in more than 19% degradation in FTL processing throughput. This degradation stems from the costly interaction between the enclave and the SSD. To access SSD on the traditional PCIe, the enclave first transitions to the untrusted part through a special function called NAND call, and then access the SSD via IO stack, and then finally returns to the enclave via another function called eCall. Each eCall and O-call incurs more than 20K CPU cycle overhead. Fortunately, the emerging CXL interconnect offers a compelling solution. CXL allows the host to directly access the SSD, which bypasses the IO stack and the costly O-call eCall function. More importantly, the new TE security protocol feature in CXL 3.1 can secure the data exchange between the SSD and the enclave, which enables the secure enclave SSD interaction. Inspired by this key insight, we propose our XHarvest, which is the high performance and cost-efficient SSD architecture. Our XHarvest rethinks the SSD architecture. It retains moderate resources within the SSD, which isolate between the SSD internal tasks such as FTL and user applications on the regular IO loads. This moderate resources provision also ensures cost efficiency. To sustain high IO performance, XHarvest utilizes the CXL-Driven, secure and efficient harvesting mechanism to cope with IO burst. Let's begin by detailing our secure CPU harvesting design. XHarvest executes the firmware within the SGX enclave, which exploits the powerful host CPU for the firmware task while protecting sensitive algorithms. Now, let's explore its IO path. First, by leveraging CXL, the enclave can directly fetch IO requests from the SSD. Then the enclave consults the FTL cache to translate LPN of the request to the flash addresses. Following this, the enclave, also utilizing CXL, directly dispatches the PPN to the flash controller within the SSD for reading or writing flash. As we can see, the IO path involves multiple host SSD communication. When the host CPU handles IO request, this raises a question: how do we achieve efficient communication without compromising security? With deep analysis, we recognize that Both the enclave and SSD are inherently trusted entities. Critical metadata in their memory remains protected. Thus, the focus shifts to securing the CXL traffic between these trusted entities. We address this concern by leveraging the TE security protocol feature. TSP begins with mutual authentication to confirm the authenticity, then encrypts the CXL traffic using the efficient symmetric encryption algorithm. This ensures the confidentiality and the integrity of the CXL traffic. Based on the secure CXL traffic, we build a efficient message processing communication mechanism for the host SD interaction. For more design details such as memory harvesting and FDL cache, please refer to our paper. We built our XHarvest design on the OME Word emulator and utilize NUMA to emulate the CXL. We compare XHarvest with multiple settings. The conventional SSD that integrates substantial internal resources, the open channel SSD, which is the SOTA, cost-efficient, and high-performance SSD architecture. For XHarvest, it retains only 25% of the internal compute power and 10% of the memory compared to conventional SSD. In macro benchmark test, XHarvest achieves 5% bandwidth increasing over conventional SSD by utilizing the powerful host CPU. Note that we don't concede the contention issue of OCSD in macro benchmark, making it an ideal case. Although XHarvest introduces SGX, it remains only 0.7% behind OCSD. We evaluate the impact of the host resource contention with real applications. We constrain the application memory in OCSD to 19% and 18% of the XHarvest to emulate the median and high contention due to its statical and excessive memory reservation. In RocksDB, XHarvest outperforms OCSD by 11% in throughput and reduces tail latency by 10%. In TerraSort, XHarvest reduces execution time by up to 2.27 times over OCSD Edge while improving 28% cost efficiency. To summarize, the cost utilization dilemma drivers cost-efficient and high-performance SD design. However, the existing OCSD and its simple extension faces challenges, including resource contention, hampered host CPU collaboration, and compromised host CPU exploitation. Inspired by the key insight from resource utilization characteristics, CXL, and TE technicals, we propose our XHarvest. Our design rethinks a new SD architecture by enabling secure and efficient host resource harvesting mechanism, successfully achieving the cost efficiency and high performance. That's all for my presentation. Thank you for your attention. I'm happy to have any question or comment.